Good morning, ladies and gentlemen. So again, by our convention, let me first see if you have any. This is a little loud, maybe. Turn the volume down a bit. Let me see if you have any questions either about the material that we've discussed today, and I actually have some for you here. We're not going to go through all of them, but these are some of the interesting topics you may want to talk about at your discussion sections, at your leisure with your relatives, now that you are armed, hopefully, with information. I can go through some of them as well. But before we do that, let me see if you have any questions about the physics topics, and then we'll talk about the upcoming midterm that happens next Tuesday. No urgent questions. Then let me first talk about logistics. Next Tuesday in class time, so that's at 9:30. Well, we'll start Berkeley time at 9:40, but please be here promptly. We have an in-class exam. Those of you who need special accommodations, please contact us if you haven't already. We will actually contact you as well. Almost everybody will be in this room. There will be two parts to the exam. There will be 20 multiple choice quiz-like questions that will be similar to the quizzes you do on the homework. They will be similar to the quizzes we do here in class, or the multiple choice questions at the end of each chapter. So there will be 20 of those. And then there will be 3 kind of short answer, free-form questions for which you will be required to write a short paragraph, few sentences. I'm going to post practice, hopefully later today. But that's roughly the setup. Now, the exam is closed book. However, you will be allowed to have a single page, 8.5 by 11 letter sized, with any information you wish to fill on that page on both sides. Any font, as long as you can read it without magnifying instruments. Well, except for prescription glasses. So any information on a single page, double-sided. If I were you, I would actually keep that page. You'll be allowed another one for midterm 2, and then you'll be allowed 3 of those for the final. So if you think about the midterm 1, we'll cover chapters 1 through 4. That is, it will cover everything that you have discussed in discussion sections in the homework, everything up to radioactivity. And then the second exam will cover everything from today's lecture, nuclear power and weapons, I think until chapter 9, if I remember correctly. And then the final will be comprehensive. So if you're writing those cheat sheets, 1, 2, 3, you'll have the 3 of them for the final. But your strategy may differ, so fill it out with any information you wish, so that if you don't feel like you want to memorize all of the numbers in the book, you don't have to. The point of this class is not to make you memorize every number, but rather have you understand the key concepts, the most important facts, and then be able to look up the information, knowing the concepts, being able to look up the information that you may need at a critical time. Otherwise, closed book, turn off phones, and everything else that's standard for any exam at Berkeley. Do you guys have any questions about exam format? Yeah? Oh, do you need to bring a Scantron? No, you don't need to bring a No, you don't need to bring a Scantron. Yes, we will use one. So the multiple choice, right? We got one? Oh, it's coming. Yes, you fill out the multiple choice on the bubbles just like the normal Scantron, whatever, SAT tests and whatnot. But you don't need to bring a piece of paper. Yeah? Are you allowed to use the calculator? No, you don't need a calculator. You're allowed to use one, you don't need one. All of the numbers, so on the multiple choices, all of the numbers should be computable to one significant digit, and therefore assuming you can multiply 2 by 4, something like that, you don't need a calculator. We will not require you to take logs or square roots. But if it makes you feel better, you can bring one, but not the calculator that's inside a smartphone. So no smartphones, but a regular arithmetic calculator. All right, any other issues? All right, so I'll repeat the same spiel on Thursday for those who either are not here yet or want more information, and I'll wish you good luck on Tuesday. So in the meantime, what we'll discuss today is effectively a continuation of the previous week. We talked about radioactivity. In fact, again, let me jump to these questions. You didn't ask, I didn't ask, but at the end, actually, if you looked at the PDF file that I uploaded under the files section on B courses, there's a list of questions that at least might interest me. Hopefully it might interest you. That's something that you may want to discuss again in the discussion sections that have, at least half of them have to do with the policy rather than the actual physics. Some of these questions obviously about physics and are interesting, like why is your wine radioactive and what is carbon dating. Apparently I recently looked up some, I forgot where. I was at a restaurant. There was a very nice 1945 wine for $45,000. Didn't buy one. I don't know why it's so expensive, but maybe because it has low amount of cesium in it. It was bottled before the nuclear weapons tests have been conducted in the atmosphere. Probably not because of that, but. So you can discuss radioactivity in the environment, but there are also some interesting policy questions that you may want to think about. For example, if you ever flown between 9/11 and now, most likely you have gone through full body scanners. If you paid attention to them, there are actually two types of full body scanners. Now, if you go through the airport, say if you go through the San Francisco and you sort of assume the pose, and the thing sort of turns and scans you, if you look at it carefully, it says millimeter wave technology. So the scanners that are now employed by TSA do not use X-rays anymore. They use basically high radio frequencies. Millimeter wave technology corresponds to wavelengths of millimeters, frequencies of sort of 50 to 100 gigahertz. Basically, these are radars. It's very similar technology to a military radar, except low power, right? It doesn't sort of cook your insides, hopefully. It also employs electromagnetic waves that have much lower energy per quantum than the energy required to ionize your atoms in your body, and therefore, it's an example of non-ionizing radiation, something that, as we discussed last time, is not known to science to cause cancer. In other words, we know that ionizing radiation does cause cancer. Non-ionizing radiation with the energy is not sufficient to ionize atoms, to pull electrons from the nuclei, are not known to cause cancer. So this is a safer technology, and as it turns out, actually is more effective in detecting stuff on the outside of the human body. It looks at the backscatter of those radio waves and can detect metal objects, can actually detect changes in the outline of the normal outline of the body, so it can look for, you can look for, I don't know, pockets of explosives. But before that, before about 2 years ago, airports employed relatively low intensity X-ray machines that looked at X-rays also scattered back from the body of a human being scanned. And X-rays use higher energy than the millimeter wave technology. X-rays is an example of ionizing radiation, and therefore those X-ray machines would actually expose every human that went through the airport to low doses of radiation, something on the order of 1 millirem, which is less than 1% of the annual dose every human receives naturally. So one can ask, if you assume a linear no-threshold hypothesis, which says that no amount of radiation is safe, and every small amount of radiation increases your cancer risk, you can compute what are the chances of, how many extra cancers one produces in a population of the US, for example. So if you assume, say, 100 million people go through the scanners every year, multiplied by 1 millirem per passenger, so that gets you, what, 100 million is 10 to the 8 people, millirem is 10 to the minus 3, so you get 10 to 5 rem human exposed divided by 2500 rem. You can figure out how many extra cancers are produced in the population, assuming linear no threshold hypothesis that, as we discussed last time, cannot be discriminated from, let's say, threshold hypothesis. It's the best we have now. So if you assume that, you would compute that roughly 40 cancers a year could be produced. Now, here's the question, and that's a policy question. It's clearly terrible to expose humans to radiation if you think you'll be generating in the 100 million passengers 40 extra cancers. It's a terrible thing to say. However, is it better than terrorism? So if you know that between 9/11 today, no acts of terrorism on US airlines have ever been successful. There have been attempts, but unsuccessful. And so no people have died as a result of a terrorism, and then you know, 9/11 killed several thousand people. So you can actually use that as a policy decision, policy trade-off. Is it better to prevent terrorism with the tool that's also somewhat harmful, or is it better to allow terrorism and not expose humans to radiation? Policy decision, and requires knowing numbers, requires thinking about it. Now, luckily, that's not a question anymore because now TSA uses millimeter wave technology that's not harmful. But it's an interesting thing to discuss. Actually, another interesting thing to discuss, you know, after Fukushima, potassium iodine tablets in the US flew off the shelves. You may think about what is potassium iodine. Potassium iodine is a basically heavy salt. Potassium is here, iodine is there, so iodine is slightly heavier than chlorine. Potassium is slightly heavier than sodium. Sodium chloride is table salt. So potassium iodine is an example, iodide, right? Is an example of a effectively heavy salt, but in particular it's useful because it has a lot of iodine, and iodine is stored in the thyroid gland. And as we discussed last week, one of the fallout products from radioactive, fission products, one of the fallout products from a nuclear accident or a nuclear bomb explosion is radioactive iodine. This radioactive iodine has a lifetime of about half-life about 8 days, but it gets stored primarily in the thyroid gland, just like regular iodine, and may cause thyroid cancer. So if you want to prevent yourself from exposure to radioactive iodine, the typical thing to do at the sites that are very close to the epicenter of the accident is to saturate your thyroid gland with normal, non-radioactive iodine so that the radioactive one doesn't get in. So these potassium iodide tablets are normally distributed to people very close to the site of a nuclear accident, such as near Fukushima or near Chernobyl. As it turns out, it's also, at least in the Soviet times, it was one of the standard issue tablets in the Soviet army for soldiers in the Soviet army, so that if they have to operate near the site of the tactical nuclear weapon explosion, they can protect themselves from the fallout too. After, this is known fact, and so as it turns out, after the Fukushima, US sources of potassium iodide at normal pharmacies were depleted by panicking population. And people started swallowing these potassium iodide tablets here in the US, even though we are 10,000 miles away from Fukushima, and the amount of radiation that we were exposed to was significantly smaller. So is this a good thing to do? Is it actually better to take this potassium iodine as a precaution if you're 10,000 miles away from the site, just in case, or is it better to not do that? Well, the answer to that depends on, if you are very far from a nuclear power plant, the answer to that depends on the level of your exposure, which we discussed last time, and we discussed also on Thursday, and whether there are any side effects from taking potassium iodide if you don't need to. There are potential chemical side effects from saturating your body with iodine. And also, as it turns out, you're taking potassium iodine, and potassium actually slightly radioactive too. So if you are very far from the site and you are not at risk of significant exposure to radioactive iodine, taking potassium is probably not a great idea. But that's another thing to discuss. All right, what we'll talk about today actually is what are the sources of man-made radioactivity. We'll talk about nuclear weapons and nuclear energy. That also has a significant number of policy issues associated both with nuclear proliferation or non-proliferation, distribution of nukes to rogue countries, as well as nuclear power. We live in Berkeley. This is the sign as you drive on, I don't know, Shattuck, for example, you see the sign. We are entering a nuclear-free zone. The Berkeley City Council has decided that the Berkeley would be free of nukes. Well, you have to read the fine print to actually understand what exactly it means. I think by the city charter, nuclear reactors are not allowed on Berkeley City, within the Berkeley City limits. In fact, there was one. There was a nuclear reactor in Echeverry Hall. You guys know Echeverry Hall, across the road, next to the Soda Hall, if any of your computer science types. Echeverry Hall until, I think, early 90s used to have a research nuclear reactor that nuclear engineering department ran for basically student education and research. It was dismantled. However, other radiation-producing machines actually allowed at Berkeley, so in particular, X-ray machines obviously have to be allowed for dental and full-body X-rays. As it turns out, fission neutron sources are allowed too, so Echeverry Hall now has a neutron generator that's been commissioned also for research. Well, this is sort of everybody's most famous known nuclear reactor operator. And do you guys know what this is? That's a nuclear power plant. You know where this is? This is outside, San Onofre, exactly. That's outside of San Diego. And that's recently been decommissioned. Or it's actually shut down. It's not decommissioned yet. It's a San Onofre nuclear power plant outside of San Diego, or between San Diego and LA. You can actually drive on the highway and see it. You see these domes from the other side. The highway is on that side, Highway 5. So nuclear power is around us, close. Actually, the closest power plant to us is called Diablo Canyon. Is near San Luis Obispo. It was designed in the 1960s, 70s. It actually came into operations relatively late in the 1990s. And the difference in time between that is not just the construction, but it took sort of over 10 years to get the authorizations to turn the reactor on after it was built. Until very recently, Diablo Canyon was the last nuclear power plant in operation, the latest nuclear power plant that came into operation. And that was until very recently. Well, it still is. It's still the last operating nuclear power plant, or the most recent operating nuclear power plant. Very recently, as in about 2 years ago, towards the end of 2011, the Nuclear Regulatory Commission, NRC, has now approved the 2 new power plants in Georgia on the East Coast that use the more modern, or the most up-to-date design, so-called Generation 3 nuclear power plant. So for the first time in about 30 years, the new power plant has been improved, and in fact, NRC has approved 2. So this is a poll. This is not a quiz that will count towards your grade because, well, there's potentially no right answer. But I would like to poll you nevertheless and perhaps stimulate the discussion about this development. So let me bring the question back here again. So given that before we discuss nuclear power, given what you know so far, what you have heard on the radio, in the news, or what you have read, do you think this is a good idea or bad? So is this, questions are that this development is great because nuclear power produces pollution-free energy and abundant energy. Question B is that we need to replace our aging reactors, so the new reactors are actually good. And then the two negative ones for various reasons, either because nuclear power is risky or because we actually know nuclear accidents happen. So let me poll you and see what you think. Give me just a sec to start the button, start the poll. And we are counting. So yeah, please register your answers. Maybe I'll give you another 5 seconds to think and click. And I'll turn it off now, and let's look at your opinions. Here's the distribution. So interestingly enough, even though we live in a nuclear-free zone, most of you are pro-nukes. That may or may not be surprising. With the justifications A and B, and in particular the fact that we need to replace aging reactors being the opinion. Now let's do an experiment. There are still some of you who are not on board. Well, some of you who may actually, have a different opinion. Now, let's turn around and maybe discuss this for a minute. See if those of you who are against nuclear power can convince those who are pro-nuclear power, and vice versa. Actually, let's see if the distribution changes. It's a sociological experiment. So again, I'll pause for a minute, let you guys talk, maybe turn around, talk amongst yourselves, try to convince each other in about a minute, kind of elevate a conversation about your opinion. Activity ceased. Let's poll again. Of course, you're welcome to discuss that afterwards as well, and we'll probably do a similar poll towards the end of this week. So I'm polling again. Register your answers. Let's see what happened. Again, there's potentially no right answer for this question, but it's a policy discussion. All right, 10 more seconds. Let's stop here and look. There's slightly fewer people. Oh, there it is. Oh, okay. I think it looks like everybody held, stuck to their guns. Distribution is about the same. I actually didn't pay attention, to be honest. I think it was about 15% before 2, the tail of the distribution. All right, so at this point, everybody kept their opinions, and that's perfectly allowed. So let me, where's my buttons? There it is. Let's actually talk about the nuclear power. And I think we'll spend most of today talking about the military applications of nuclear power, that is the destructive, and then we'll talk about constructive applications on Thursday. So, part of that question, part of that poll was that, nuclear power is potentially interesting because of exactly this table, because per gram of nuclear fissionable material, or even better, per gram of the nuclear fusionable, if that's the word, material, the amount of energy released in by a gram of nuclear fuel is significantly larger than the amount of energy released in any other sources, primarily chemical sources or mechanical sources like meteorites. The main reason for this has to do with the fact that nuclear fission or nuclear fusion releases energy that is contained in the binding of protons and neutrons, elements of the nuclei inside the nucleus. Nucleus is significantly smaller than the atom. Its binding energy is significantly larger than the binding energy between electrons and the nucleus itself. So chemical reaction that releases the binding energy between electrons and the nucleus releases less energy than the binding energy that's released in the nuclear reactions. And the difference is roughly a factor of 1,000,000. And so per gram of fusionable material, most of the significantly large amount of energy is released in nuclear reactions compared to chemical. Basically, chemical transformations deal with electrons. Electrons are light. Electrons are loosely bound to the nucleus. Nuclear reactions deal with the nucleus, that's where most of the mass of the nucleus comes from, most of the mass of the material comes from. That's where most of the binding energy is. So if you can harness that energy, then you can potentially have a significantly more energetic, significantly longer lasting energy source. How does this work? Well, the key to, there are two types of nuclear reactions on that page. There was nuclear fusion and nuclear fission, and we'll discuss both. So for now, we'll consider it a nuclear fission. Nuclear fission is basically an explosion. It's a breakup of a nucleus into smaller parts. And the nuclear fission reactions typically proceed by some stimulus. The most common stimulus is a neutron. A neutron is basically like a little nucleus itself. Well, it's part of the nucleus. A neutron is an electrically neutral particle that has about the same mass as the hydrogen. Nucleus is a proton. So these neutrons can travel around in the material. They're electrically neutral, therefore they don't interact with electrons and can scatter in the material until they meet a heavy nucleus. And if they are absorbed by the heavy nucleus, the nucleus can break apart. So that can be stimulated by a fast neutron or a slow neutron, depending on the type of the reaction. But what often happens is that when this nucleus breaks apart, these nuclei, these heavy nuclei that are sitting on the bottom of the periodic table, have significantly more neutrons than protons in them. And so any nuclear breakup will typically release more neutrons. And so if you started with a single neutron that stimulates, kind of catalyzes, like chemical catalysts, a nuclear reaction, breaks the nucleus apart in the process of breakup, more neutrons can be released, and then some energy. So this energy is typically in the form of kinetic energy, speed that is given to the neutrons and to the remaining fission products, remaining nuclei, but there's also some gamma rays as well. So there are two key parts to this. One is a lot of energy is released, a lot of energy per elementary reaction can be released. That energy is measured in mega electron volts. So it's equivalent to about 1,000,000 times the typical chemical energy released in a typical chemical reaction. But more importantly, multiple neutrons are produced where a reaction is stimulated by a single one. So what it means is that if you allow for this reaction to proceed further, and in fact, if you allow for these neutrons to stimulate more fissions, you can produce a chain reaction. You can produce a multiplicative effect whereby more neutrons are produced at each reaction stage that stimulate more fission, that in turn produce more neutrons that stimulate more fission, etc. So you can have a reaction, again, that's stimulated. You can also have spontaneous reaction, although the spontaneous reactions typically, so the natural fission of uranium-238 does happen, except that uranium-238 lifetime is several billion years, so the nature of the activity, nature of fission happens extremely rarely. In most power plants and nuclear weapons, a stimulated reaction happens. And so the key part to the deciding how the reaction would proceed and whether it would proceed to an explosion or whether it will fizzle depends on this one number that's called criticality. And that is determined by how many neutrons are produced and absorbed at each subsequent stage of a nuclear reaction. These nuclear reactions, so let me basically look at this, essentially work if the reactions are supercritical, like this. If each stage in the reaction produces multiple neutrons, the entire reaction and the number of fissions per second or per unit of time works essentially the same way as in finance compounding interests work. You know that if you want to earn some money in the market or by depositing your money into a bank, you look for a deposit mechanism that gives you large annual percentage yield, gives you a non-zero yield on your investment. So what you want is you want to deposit $1 into a bank and get maybe 10 cents back every year on that dollar while keeping that dollar in the bank. 10 cents for every dollar is a great annual percentage yield. If you can deposit $1 and every year get $1 back while keeping that dollar in the bank, so if your yield is 100%, that's even better. If you can get $2 back, that's great. And then if you leave your money in the bank every year, say your annual percentage yield is 100%, every year the amount of dollars double. Second year, you quadruple your investments. Third year, your investment grows by a factor of 8, etc. It's a great investment. Supercritical reactions work exactly the same way. If at every stage of the reaction, you double the number of neutrons produced, and those neutrons are all absorbed, and those absorbed neutrons can stimulate further reactions, the rate of the reactions, the number of nuclei participating in the reaction, grows exponentially and grows extremely quickly. If every step you double the number of fission reactions, the reaction rate grows exponentially. And it's exactly the same way as growing your investment, except the coefficient, the speed with which the reaction grows, is significantly faster. Of course, this is how the bombs work. You want the bombs to explode very quickly. and release a lot of energy in a short amount of time. And for that, you want a very supercritical reaction that causes all of your fissionable material, or most of your fissionable material, to react. If you're operating a nuclear power plant, you don't want it to explode, typically. And so you operate it in the regime called critical regime, where the number of neutrons produced and absorbed is constant in time. That is, for every nuclear reaction, one neutron causes a nuclear reaction, and one neutron typically comes out, and the rest of them are either absorbed by some absorber and don't participate in the nuclear reaction, or are allowed to escape. And then the so-called subcritical stage is where you actually want to shut the reaction down, and in fact, you want to absorb more neutrons that are produced for each stage of the reaction. And so this is typically what happens in the cold reactor shutdown. So if you're operating a supercritical reaction, as in nuclear explosion, it's otherwise known as a chain reaction. That causes, as I said, a very fast multiplication, very fast exponential increase in the number of neutrons produced, and therefore a very fast exponential increase in the reaction rate, in the number of fissions per second. And this is the power of the doubling. So the number of fissions per each step grows as 2 to the power of number of steps if in each reaction you produce 2 neutrons. So 1 neutron stimulates the initial reaction. The second stage, you produce 2 extra neutrons. Oh, actually, 3 is shown here. Suppose you produce 2 neutrons at each stage and then 2 neutrons in the subsequent stage, and the reaction rate grows as a power of 2 to the power of number of steps. And in certain reactions, the number of neutrons increases even faster. So in 100 steps, you can produce 10 to the 30 fissions. And if each step takes a short amount of time, say about 10 nanoseconds, for neutron to kind of rattle around and find another nucleus, 10 nanoseconds is 10 billionths of a second multiplied by 100 steps in about 10 to the minus 8 seconds times 100. So in about a microsecond, 1 millionth of a second, you can produce 10 to the 30th fission reactions. 10 to the 30 is a huge number. A typical bomb, would have several kilograms of fissionable materials, much less than 10 to the 30 nuclei. So you can explode something like this extremely quickly if you allow the reaction to proceed supercritically. I have a demonstration here. I have a demonstration nuclear bomb. Of course, no nuclei are actually involved. It's a little contraption that uses mouse traps. And I have an external device, a neutron. So each of these mouse traps you see has a couple of balls on it. So if a mouse trap is triggered, 2 balls would be released into the environment. And those 2 balls can trigger additional mouse traps. So a single ball is equivalent to a single neutron. A single mouse trap is equivalent to a nucleus that breaks apart and generates 2 neutrons at each step. And so if I, right now, this bomb sits here intact, there may be spontaneous fission. Uranium spontaneously fissions, once on average every few billion years. So we can sit here and wait for one mouse trap to just spontaneously trigger. It's not going to happen soon. But if I introduce a neutron into the volume, it will trigger one mouse trap that will generate 2 balls. Those 2 balls will trigger 2 more mouse traps, generating 4. 4 balls will trigger 4 mouse traps, etc., until every device is triggered. The whole process will end very quickly. And that's it. So this is an example of chain reaction, where a single external stimulus can generate a very fast reaction in the entire volume. and in this case, triggers all of the mousetraps in a few steps, maybe it's sort of 10 or so. Now, in order for this to happen, we can switch back to the screen. In order for the chain reaction to proceed, two things need to happen. One is each reaction, each nuclear fission has to release more than one neutron. 2 is good, 3 is better. The second thing that has to happen, each of these neutrons that's released has to be absorbed by another nucleus of the same type. So you have to arrange your material in such a way that these neutrons don't escape somewhere, that they actually are absorbed by the same nucleus. And that's not that easy, as it turns out. Luckily, that's not that easy. That's not that easy is because neutrons actually travel quite far. Neutrons are electrically neutral particles, and they are highly penetrating. If you saw a picture of that nuclear reactor that I showed last week, I can look, stand over a water pool or a research nuclear reactor. That reactor produces neutrons. Those neutrons are absorbed by meters of water that's between me and the reactor core. So neutrons travel relatively long distance. You need meters of water to shield humans from the neutron radiation, or you need meters of concrete to stop neutrons. So neutrons generally penetrate quite far. In uranium, the mean free path, that is the distance between the two interactions of the neutron, typically the amount of material you need to stop the neutron and make it absorb in another uranium nucleus, is about 17 centimeters. That's a foot and a half, like this big. So if you have a slice of a material that's thinner than that, most of the neutrons will escape. And so the reaction will be potentially subcritical. Each uranium-235 reaction produces 2.4 neutrons per fission. Plutonium-239 produces slightly more, 2.7 neutrons per fission, averaged over various stages of a nuclear reaction. So these are averages. And uranium is very dense. Uranium is low in the periodic table. It has a density of, now I'm trying to remember, I think 17 is so grams per cubic meter, more than 10, definitely. It's one of the heaviest natural elements. And yet, neutrons can still penetrate through 17 centimeters of that stuff. So if you have a thin amount of material, the neutrons will interact rarely and may leak out of your enclosure. But if you collect at about 17, a foot and a half sphere of uranium, now the neutrons produced will be absorbed in the same sphere and can cause the reaction, can produce more neutrons that can then reabsorb in the same sphere. The sphere of that radius is called the critical, well, rather diameter. The sphere of the diameter is called the critical diameter, and the mass of that amount of uranium is called the critical mass. This corresponds to about 52 kilograms for uranium-235, much less so for plutonium because plutonium is denser. And the interaction cross-section for neutrons is higher. So the critical diameter for plutonium is smaller, critical mass for plutonium is larger, is smaller, 10 kilos of plutonium, 52 kilograms for uranium. So if you have accumulated 52 kilograms of highly enriched uranium-235, you're in business. Put this together and the stuff explodes. The good news, of course, is that if you have less than that, the amount of material less than about 52 kilos of uranium will not spontaneously explode. And so you can keep this uranium in safe storage, sort of, few kilograms at a time in relatively safe chunks. Of course, during the Manhattan Project, this was calculated very carefully, the amount of material needed to stimulate spontaneous fission, and the chain reaction was calculated very carefully. And so that workers who worked with highly enriched uranium plutonium could be safe. even though accidents still happen. At one particular instance, the two halves of uranium sphere came into contact with each other, starting a chain reaction. The worker who was performing this operation, whose I think name was Harry Daglian, actually worked with plutonium-239, stopped the reaction very quickly, but still was exposed to lethal amount of radiation. So point being is that if you assembled a critical mass of fissionable material, uranium or plutonium, spontaneous explosion happens. So this also tells you how to design a nuclear weapon. If you have, well, it tells you two things. One is, in order to have a nuclear weapon, you need to have a larger number of fissionable material. 235 uranium in the sort of tens of kilograms, and about 10 kilos of plutonium-239. There was a question? No? And the second thing that you need to have is you need to assemble it in a compact object that has a critical mass. So there are two typical designs of nuclear weapons. One that's called a gun design that's typical of uranium-235 bombs. This was the first nuclear weapon ever exploded. This was the, well, ever exploded of a population center. In fact, the design is so simple, no tests before Hiroshima was done with this bomb. It's the plutonium bomb that's a little bit trickier and therefore needed testing. Uranium bomb is sort of by design is relatively simple. It's so-called gun barrel design where you have a conventional explosive that accelerates 1/2, roughly or slightly more than 1/2, of the critical mass amount of the fissionable material. It accelerates it towards a cylindrical target, which has the other half of the fissionable material. So each of the halves doesn't fission, doesn't generate chain reaction by itself, because each amount is less than the amount of the critical mass. When you combine the two together, explosion happens. So you start the reaction by conventional explosives that combines the two halves of the nuclear bomb core, and then the fission reaction, the nuclear explosion takes over. You can actually improve the efficiency of this design by placing neutron reflectors around the explosive core that will actually increase the number of neutrons absorbed and therefore reduce the amount of critical mass needed. But to first order, if you collect 50 kilos of the stuff and combine it together, the bomb explodes. So this is the first bomb dropped on Hiroshima, and that had a yield of about 10 kilotons, or a little bit more, 15 kilotons of TNT, or equivalent to about 15 kilotons of TNT. Very simple design, doesn't require a lot of engineering, but requires a large number of uranium-235. And we'll talk about how you get uranium-235. A little more complicated design that requires less fissionable material is a plutonium bomb. This was the Fat Man bomb dropped on Nagasaki. This was also the bomb that was tested first by the US. It uses plutonium, and therefore plutonium requires smaller amounts of fissionable material. On the other hand, plutonium doesn't exist naturally. Plutonium needs to be generated in the nuclear reactors. So there's a trade-off in terms of enrichment of natural uranium versus generating fissionable plutonium. The design uses conventional explosives that compresses the plutonium core to the point where the critical radius is reduced, where the explosive plutonium core forms sufficiently dense medium enough for the critical reaction to proceed. The bomb also has a number of neutron reflectors that are made out of beryllium to again increase the number of neutrons absorbed in the plutonium core. This design is much more complicated to generate or to produce and to actually make work. from the engineering point of view, because it basically requires a very sophisticated design of the conventional explosives that would generate a shock wave that exactly is focused towards the center and compresses the core uniformly rather than just blowing it apart into pieces. So, much more difficult to build, therefore requires testing, therefore requires relatively sophisticated engineering. At this point in time requires sophisticated nuclear calculations on supercomputers.